Hello friends, welcome to this session. Today we are going to study the topic type of the strain. First of all, strain. What is meant by strain? Strain, it is a measure of deformation produced by application of the external load, or it is also called as the elongation per unit length. Strain denotes by Greek letter epsilon. So actually the strain is the measurement of the deformation. Deformation may be produced in any direction. It may be in the x direction, it may be in the y direction, or it may be in the z direction. So after that we will see the different types of the strain. First of all, the linear strain. Change in the dimension per unit original dimension is called as a linear strain. When the deformation or extension it is produced in the x direction, that type of the strain we can call it as a linear or longitudinal strain. So linear strain is equal to change in length divided by original length. So symbolically we can represent strain by epsilon. So epsilon is equal to delta L divided by L. Here it is a delta L is a change in length or change in extension or change in deformation, divided by L is the original length. So you can see in this particular figure, so there is a original uniform cross sectional bar is there, whose original length is L, and after application of the load or after application of the pull on both the sides there is extension. So particular amount of extension it produce after application of the load. After that, second type is the lateral strain. The lateral strain may be defined as a change in the lateral dimension per unit original dimension. So from the linear strain to lateral strain, when the deformation it is taken place in the y direction, in another direction exactly opposite to the x direction, that type of the deformation or that type of strain it is called as a lateral strain. So you can see the lateral strain in exactly opposite direction, change in lateral dimension to the original dimension. Suppose B is a lateral dimension, so delta B divided by B, it is a lateral strain. So if extension is taken place in longitudinal direction, the shortening of lateral dimension taken place, and if a shortening is taking place in longitudinal direction, extension taken place in lateral direction. So that is the exactly opposite nature is there. When extension is taken place in longitudinal, shortening of the lateral dimension, and if shortening is taken place in longitudinal direction, extension is taken place in lateral direction. So you can see in this particular figure, so there is a shortening of the length. So original length is much higher than much higher. So after deformation or after application of the pushing type of the force, you can see there is a shortening of this particular amount. So there is a shortening of the length, it is mentioned in dotted line. So in this particular figure you can easily see that there is a upper figure is the example of the extension when in the pulling type of the force is applied on both the direction. So there is a extension, mean there is a increase in the length in the longitudinal direction, and exactly opposite there is a shortening of the lateral dimension. So you can see this shortening of the dimension B dash, and below of the figure if the pushing type of the force is applied, so there is a shortening of the length. So this delta here it is mentioned that shortening or there is a deformation here it is produced. When changes in the longitudinal direction is taken place, changes in the lateral direction also taken place. So the nature is exactly opposite, lateral direction and longitudinal direction. When appropriate force, whether it is pulling or pushing type of the force is act onto the uniform bar. After that, the volumetric strain. When member is subjected to stresses, it undergoes some deformation to all the direction. Means whenever there is a forces or load is acting onto the any particular body or member, at that time there are stresses are produced. So because of the stresses there is a deformation is happen into the body in all the direction, and whatever the changes is happen into the member, in all the direction, so that changes, that will be the change in the volume. So if you define the volumetric strain, the ratio of change in volume to the original volume is called as a volumetric strain. So symbolically it is represented by epsilon v is the volumetric strain. So delta v divided by v, delta v is the change in volume and capital V is the total volume. So epsilon v, we can also write delta L in the x direction. Suppose extension it is taken place L, so delta L is change in extension, plus delta B is a change in lateral dimension suppose in the y direction, and delta D suppose the depth in the third direction. If it is a change is happened at that time, you can also take that third direction also. So these are the x, you can see into the figure also, in the x direction length, y direction B, and z direction D. So length, breadth and depth, whatever the changes happen or deformation is taken place, so that we have to take for the total calculation of the change in volume or volumetric strain. So where the epsilon v volumetric strain, delta v change in volume, v is the original volume. In general, for any shape, volumetric strain may be taken as a sum of strain in all the three mutually perpendicular direction. Poisson's ratio, the ratio of lateral strain to linear strain. So up till now we studied the lateral strain and linear strain also. So Poisson's ratio is the ratio of lateral strain to linear strain within elastic limit. So this particular word is important. Whatever the proportional limit is there, or within elastic limit, that strain is directly proportional to the strain. So it is denoted by mu or 1 divided by m. So mu, Poisson's ratio, also we can write lateral strain divided by linear strain. So lateral strain can be represented by epsilon LT, that is a lateral strain, divided by epsilon L means linear strain. So in this figure you can easily see that there is a deformation after pulling forces are applied. So it is a material dependent ratio. This Poisson's ratio is also called as material dependent ratio, and normally this value is in between 1 by 3 to 1 by 4, that is 0.25 to 0.35, and for the steel that value become 0.3, and for concrete that value become 0.15. The lateral strain proportional to axial or linear strain in elastic limit, provided that material is both homogeneous and isotropic. So this proportional limit is only exists when the material or member we assume or it is in homogeneous or isotropic nature, then and then this particular proportional limit is applicable. Homogeneous, already we know that material having the same elastic properties or composition at every point in the body, that type of the material is called as a homogeneous material. And isotropic material, that if the material is having same elastic properties in the all the direction, that particular property it is called as a isotropic material. So this homogeneous and isotropic property is one of the requirement for the material. Then and then we can finding out the Poisson's ratio. So then and then we can say that lateral strain proportional to the linear strain. So in the elastic limit, this is a mandatory that material should have the property homogeneous and isotropic in nature. Factor of safety. In practice, it is not possible to design a mechanical component or structural component permitting stresses up to ultimate strains. So for the following reason. So normally at the time of designing, we cannot directly take the ultimate stress for the design purpose, because of there are some reasons are there. Whenever we are calculating the ultimate stress, the reliability of the material may not be 100%. We cannot 100% rely on to the material, and the loads taken by designer are only estimated loads. So that whatever the loads are calculated or estimated, that are estimated loads. So unexpected impact and temperature loading may act. So incidental and accidental loads may occur into the material. The resulting deformation may obstruct the functional performance of the component. So this is also one of the reason. Calculated stress will not be 100% real stresses. So whatever the calculation part is there in the office, and actual in the practice on the field, the 100% real session, it will not match. The calculated stress and 100% real stress will not match. So hence the maximum stress to which any particular member is designed is much less than the ultimate stress. That's why at the time of designing we are taking the stress which is a below of the ultimate stress or less of the ultimate stress. That particular stress, it is called as a working stress. So for the designing of any particular member, it may be a structural or maybe a machine part, so we are taking the working stress. That working stress value is less than ultimate stress. That's why the factor of safety we can define, it is the ratio of ultimate stress to working stress, that it is called as factor of safety. So here it is, factor of safety is equal to ultimate stress divided by working stress. So factor of safety, some of the important material are mentioned below, depends upon their reliability. So for steel, the factor of safety is generally taken as 1.85, and for concrete that factor of safety is 3, and for timber the factor of safety 4 to 6 it is taken for the construction of any structural member. So for the today's session we are completed this. Thank you very much.